This is going to be a very short review on enzymes. Enzymes are necessary for life because most biological reactions happen too slow. Enzymes really increase the speed, sometimes 1,000 times. All enzymes are actually proteins regardless of what they work on. So an enzyme might work on a sugar, but it's still a protein. And what it basically does is convert something from, now in this diagram here they have reactant, but we like to work with the word substrate is a little better. So it changes a substrate into a product here. Now in this particular situation you can see on the energy curve that we're losing energy when we go from the substrate to the product. When you lose energy, gives off energy, that's called an exothermic reaction. Now be careful, biology likes to have multiple words for the same thing. Sometimes that's called an exergonic reaction. They basically mean the same thing. But here's the deal. In order to go from substrate to a product, things just don't go automatically. You have to go over a little bit of energy you got to put into it to start it. Think about it like a gasoline can. It doesn't explode spontaneously. You have to give it a little match. You got to put in a little energy. That's called the activation energy. And usually, the amount of activation energy you need is so great that the reaction really doesn't happen unless you go ahead and somehow lower the amount of energy that you need. So how are you going to lower that? By adding an enzyme. And what an enzyme actually does is, I'll just draw it right here, is it would lower the activation energy you need. So instead of having to put in that much to go over that hill, maybe it's much smaller and it goes like that. So you would lower the activation energy. You don't need this, you just need this little bit right here. Now it could happen the other way too. In this case, when we go from our substrate or reactants to the products here, you're actually increasing the amount of energy. So the products have more energy. You're putting energy into it. That could happen too. That's called an endothermic reaction. Once again, we have multiple words for the same thing. Sometimes that's called an endergonic reaction. Let's see if I can straighten that out. Basically the same thing. And you still need to put energy into it. So you still need the activation energy, but this time the activation energy is much, much bigger, right? So to go from here to here, we got to push up, and then the reaction automatically takes place and it goes down. What does an enzyme do? Does the same thing. It decreases the amount of activation energy you need. So instead of going up here, maybe we just need to go like that to get there. So you just need that activation energy. Once again, you decrease the activation energy and that speeds up the reaction. And how does it decrease the activation energy? By forming a complex where it joins up and bonds enzyme to substrate. This is called the lock and key model. That's the simplest way to explain it. Basically, it means that one enzyme fits with one substrate. So I've used E and S here for my letters, E for enzyme, S for substrate. The two of them are separate. Here they're separate right here. They come together and they bind. Now where do they bind? In a special area here. This special place there is known as the active site. Let's see if this is the active site where the substrate will bind in there, and so it increases the surface area by binding it. Now while it's all bound up there, it actually lowers the energy level. So ES is a transitionary state that lowers the energy. That's why the activation energy goes down. And while it's all locked up in there, right, it actually is changing it physically into a product. And then it releases it. So the guy who gets released here was not the guy we started with. We started with a substrate, now we're left with a product. Now the interesting thing here is the substrate gets all used up, but what happened to the enzyme? Nothing. It got released again. So the enzyme can go back to the beginning, right? And it can bind up to another substrate. So the enzyme keeps recycling, using more and more substrate, producing more and more product. Lock and key model. The basic idea is that there's only one shape of a substrate that fits into the enzyme, and that's why it's so important for that enzyme to have tertiary structure. When we talked about primary, secondary, and tertiary structure of proteins, using a certain sequence of amino acids, it then generates that active site where it can bind in there. Okay, now sometimes it needs a little help to get in there. So in this case, the substrate doesn't match the entire active site. It just matches this part there, but to get in there, it needs a little bit of help, just like a shoehorn kind of fitting your foot into a shoe. And this guy helps it to get in there, and that guy is what we would call a cofactor. So a lot of times with enzymes, you really have to add somebody else in there to kind of make them work at their maximum rate. Unfortunately, most enzymes probably don't work with lock and key. In other words, there are many enzymes who could work on several different substrates. How is that possible? Well, here's a different model. This is called the active fit model, which basically means that the shape of the active site will change a little bit. Not a whole bunch, but a little bit. So if you take a look here, right, all these guys wouldn't fit in there, right? But this guy actually can't really fit in there by itself, but it's close, right? So this little piece matches with that, but it doesn't match with this guy over here. So what happens is the enzyme itself changes its shape. See, it's a little round here, and then it becomes triangular, and then the guy can fit in. So induced fit means that it's a little flexible. So you could have multiple substrates that are close that could kind of fit in there. And then when it's released here as a product, there's our product, the shape then returns to what it was in the beginning. So it's flexible. And I'm going to guess that most enzymes probably work on the induced fit model. Okay, hopefully that should bring us back up to speed with what enzymes are all about and the basic models of how they work.